My name is Chris. I'm the computational auditory neuroscientist here at Resonance Medical. Today I'm going to be demoing some of the optimization software we've been developing over the past couple months. I'm going to show you three main strategies that we've been using. And what I've done is actually simulated a type of unideal cochlear implant fit by removing a couple of the auditory filters that correspond to electrodes in the lower frequencies. So let's get started. This is the first interface we're using to perform the optimization. And the way it works is the subject presses start, and they'll hear a word, and they're going to click around this black square. And what each dimension along this black square corresponds to are two parameters that belong to a particular function that manipulates the auditory filters in a specific way, such that if you click around this black square, you're able to hear the sound processed in very different ways. And so let's just see how, or take a listen here.
Key. Four.
So you click around, and you can sort of get a sense of what part of this parameter space sounds good to you. So compared to like over here, this sounds more clear. And then you find a particular spot that you like, and press accept. It goes to the next word. And so the real advantage of this method is that we're able to compare a large number of parameters essentially in parallel. And so let's just try this.
Rec.
Okay, so it looks like over here this time.
Rec.
Sounds better. And so the subject, or I would accept this one, let's say. And so the subject will do this for 20 to 30 minutes. And what the algorithm will then do is take all of the points in the space that the subject accepted, then it estimates the distribution over those points, and then the most probable value on that distribution is suggested as your, in this case, center frequencies. And so we can do the same thing for bandwidths, for gains, or anything really that we'd like. And so that's essentially how this particular approach works. Our next approach involves something called an interactive genetic algorithm. And the way it works is that the subject will hear a word played in, let's say, 5 to 10 different ways, or with 5 to 10 different set of parameters. And about half of these parameters will be similar to the original settings of the cochlear implant patient. They'll be drawn stochastically, but around those original settings. The other half will be drawn totally at random. And so then the subject will hear these words, and then they're going to rate them on how bad or good they thought they sounded. And so let's just see how this works.
Jug.
Okay, but it sounded a bit tinny, so we can put that here.
Jug.
Okay, I like that one quite a bit more.
Jug.
That one, yeah, I like that one as well.
Jug.
That one is pretty similar to these, but maybe a little bit worse.
Jug.
Ooh, that one was a bit way too bassy, I'd say, so I'm going to put that one down here.
Jug.
That one was pretty good, but I didn't like it quite as much as these three.
Jug.
And that one wasn't very good.
Jug.
That was okay. And so what happened there was the algorithm took the set of parameters that had the best ratings and then recombined those in a stochastic way to create children. And now the children will be played and we'll rate those. And so this is called an interactive genetic algorithm because the fitness function here, or what determines what of the parameters make it to mate, as it were, are defined by user input. And so we can do this again.
Sob.
It was okay, not very good.
Sob.
A little bit better.
Sob.
Not very good, kind of bassy.
Sob.
Tinny, none of these sound very good. We're going to keep them all down here.
Sob.
Okay, I like that one.
Sob.
That one sounded even better.
Sob.
That one was pretty good too.
Sob.
And that one was not as bad as these, but not as good as these three. And so the real advantage with the genetic algorithm is that there is a lot of stochasticity, so you avoid things like local minimum, but it's still driven by the user. And so eventually, what we find is that the children that are being produced by these parameters all tend to sound quite good. And so we assume that we found a spot in the parameter space that appeals in general to the user. This last technique we're using to perform optimization is inspired by a relatively recently formulated problem in machine learning called the dueling bandits problem. And the basic idea is that if you have a large number of parameters drawn, let's say at random from the parameter space, how do you determine which one is best when the only action you can perform are these binary comparisons between pairs of parameters? And so these are what are called duals. And so the idea is that if you take the winner of these duels in aggregate, they should correspond to some statistic that's predictive of a good set of parameters. And so we can put a distribution over our best estimate as well. And as the algorithm proceeds, this distribution will get tighter, and we're actually drawing our parameters to present to the user from this distribution. And so after a sufficiently large number of trials, this converges on a specific area of the parameter space, and both of these options will sound similar but both good. And so let's just see how this works.
Van, van,
Okay, we can
van,
repeat it.
van,
All right, this one's maybe a little bit better.
dead, dead,
I like this one more.
seize, seize,
Definitely this one.
wreck, wreck,
I like this one.
tooth, tooth,
So it's kind of similar to what you do when you go to the optometrist, right? Where you're looking at these set of letters in the back and using different lenses, and you're telling the optometrist which one is more clear, and he's able to use these questions to pinpoint the best prescription for you. And so it's, in principle, at least on the surface, similar to that.
tooth, tooth,
And so that's the idea.
jug, jug,
And if they sound similar, if they both sound bad, you can always press the equal sign. The algorithm will ignore those data points.
sun, sun,
So as you can see, this can proceed quite rapidly. In fact, a subject can go through a few hundred of these in 20 to 30 minutes, which is sort of the time frame we're looking for to perform on the optimization. In our testing, this has done quite well in suggesting parameters that sound optimal. So those are the three main optimization strategies we've been taking to tackle this problem. So what I'm going to do now is play a couple sentences. The first, recall, is a simulation of an unideal cochlear implant fit where I've removed some of the auditory filters corresponding to electrodes in the lower frequencies. And the second is the optimized version where we've compensated for that unideal fit. So let's take a listen to see how those sound.
The boy went to bed early.
the boy went to bed early.
So hopefully it was obvious that in the second sentence we've recovered those lower frequencies. And so with either or with really any one of these strategies that I presented, we do get similar results, and it always sounds better at the end.